The most dangerous thing on the Sun this week is not the explosion that already happened. It is the one that hasn't. A week ago, forecasters pointed at a sunspot rotating into view and named it as a threat. It has since swelled into the largest region on the entire face of the Sun and twisted into the configuration that produces our star's most violent flares. Its smaller neighbour has already fired an X-class flare and hurled a cloud of plasma toward Earth, timed to arrive on the 4th of July. But the giant we were actually warned about is still sitting there, silent and fully loaded, turning slowly toward the one position from which its next shot would be aimed straight at us. If you want to follow this as it unfolds, hit the like button and subscribe to the Sky Lab, because we are going to track this region every single day it stays in view, and you will want to know the moment it moves. Tell me in the comments where you are watching from, and whether you have ever seen an aurora with your own eyes. Now let's get into it. Part 1. The Sunspot. We were told to watch. A week ago, we pointed at a small dark bruise rotating onto the edge of the Sun, and we told you to remember its number. At the time, it was nothing to look at. It was a smudge crossing over the eastern limb, one of dozens of features that come and go on the solar surface every month, and if you had glanced at the Sun that day through the proper filters, you might not have given it a second thought. We flagged it anyway. We told you that this one, sunspot region 4478, was rotating into view, that it carried the early signature of a delta region, and that it was worth watching as it turned to face us. That was June 25th. It is now July 1st, and I need to tell you what that smudge has become. It is now the single largest sunspot group on the entire face of the Sun. Not one of the largest, the largest. In 6 days it grew into a sprawling magnetic complex wide enough to swallow the Earth several times over, and as it grew, it did the one thing we were afraid it might do. It crossed the line from a simple magnetic region into the most dangerous configuration a sunspot can have, the configuration that produces the strongest explosions our star is capable of. And while all eyes were on that big, slow, quiet monster, something happened right next to it that changed this from a story about a spot we were watching into a story about a shot that has already been fired. Its neighbour went off. Late on the evening of June 30th, a second region sitting just to the north, region 4479, released an X-class solar flare. If you take nothing else from the next 2 hours, take this. X-class is the top of the scale. It is the highest category of flare our Sun produces, the same class of event that has, in the past, knocked out radio across half the planet and pushed power grids to the edge of collapse. This particular flare was an X1.1, which is the floor of that top category rather than its ceiling, and I want to be honest with you about that from the very start because this channel does not trade in panic. But a flare is only the flash. The flash is not what reaches across 93 million miles of empty space and touches the world you're standing on. What does that is what the flare threw off behind it. And this flare threw off a cloud. Not just any cloud. A full halo coronal mass ejection, a billion-ton eruption of magnetized plasma torn loose from the surface of the Sun, and the word halo is the part that should make you sit up. When one of these clouds erupts sideways off the edge of the Sun, we see it as a lopsided smear heading away from us into space, and we breathe a little easier. When we see it instead as a complete ring, a halo expanding evenly in every direction around the black disk of the Sun in our instruments, it means one of two things. It means the cloud is heading directly away from us, out the back of the Sun where it can do no harm, or it means it is coming directly at us. This one erupted from a region almost dead center on the face of the Sun. The part pointed straight at Earth, and the forecasters have already done the math on where it is going. Their answer is that it arrives here on the 3rd or 4th of July. Read that date back to yourself. The cloud thrown off by the strongest kind of explosion our star can make is scheduled to arrive at Earth on the 4th of July. So let me introduce you properly to the two characters in this story, because for the next couple of hours they are going to matter more to you than almost anything else happening on this planet. The first is region 4478. That is the one we warned you about a week ago. It is the giant, the largest spot group on the Sun, and it is strangely the quieter of the two. The second is region 4479, sitting just to the north. It is smaller. It is also the one that just fired the X-class flare and hurled that cloud at us. And here is the detail that has been quietly gnawing at me since the numbers came in. the detail we are going to keep circling back to all the way to the end of this video. The one that fired is the smaller one. The big one, the one we were warned about, the one large enough to be seen as the dominant feature on our star, has not yet let go. Think about what that means for a moment. The shot that has already been fired, the cloud already racing toward your 4th of July, came from the second string player. The heavyweight is still standing there, still turned toward Earth, still holding whatever it is holding. We will come back to that. I promise you we will come back to that, because it is the whole reason this story keeps me up at night in a way an ordinary solar flare does not. But first I owe you the part of this that I find genuinely remarkable, and it is not the flare, and it is not even the cloud. It is the calendar, because forecasters saw this coming. A week before any of this happened, the space weather community looked at that smudge rotating over the edge of the sun and identified it as an incoming delta region, a spot to keep eyes on. We told you the same thing on this channel on June 25th, and then the region did precisely, methodically, exactly what a region like that is capable of doing. It grew, it complexified, its neighbour erupted. The warning was not vague, it was not a horoscope. It named a specific object on the sun and said, "Watch this," and the object delivered. That almost never happens with this kind of clarity, and it reframes the entire event. This is not the sun surprising us. This is the sun doing something we saw loading a week out, on schedule, in plain sight. Which raises a question that is going to sit underneath everything else we talk about tonight. If we were warned, if we saw it coming, if the region announced itself a week in advance, then what exactly are we supposed to do with a warning like that, when the trigger is a nuclear furnace 93 million miles away that answers to no one and nothing? Hold that question. We are going to earn our way to it. Let me give you a sense of scale, because numbers like largest region on the sun can wash right over you if you have nothing to hang them on. Region 4478 covers an area on the solar surface measured at roughly 1450 millionths of the visible solar hemisphere. That is the technical unit, and it means nothing to you and me on its own, so let me translate it. A region of that size is wide enough that you could line up several planet Earths across it, and still have room left over. If the sun were a basketball, this would not be a freckle. This would be a continent drawn on the ball in ink you can see from across the room, and it is not a smooth, calm continent. It is a tangle. It is a place where the sun's magnetic field has been twisted and knotted and crushed together, until North Poles and South Poles are jammed into the same small space, straining against each other like two ends of a spring wound far past where it wants to sit. That strain is stored energy. That stored energy is what a flare releases when the whole tangled structure finally snaps. And there are two of these on the sun right now. That is the part the forecasters keep circling in their own discussions, the part that is genuinely unusual. Having one region wound up into this delta configuration at any given time is notable, but not rare. Having two of them at once, both large, both facing our direction, both carrying a standing 1 in 10 daily chance of firing off another one of those top-tier X-class flares, is the kind of setup that makes people who watch the sun for a living choose their words carefully. Two loaded structures. One has already gone off. One has not. Now, I've thrown a lot of numbers and names at you already, and over the next hour and a half I'm going to give you many more, because that is what we do here. We go to the actual data, and we let it speak. But I do not want you to lose the thread underneath all of it. So let me say it once, cleanly, the way I would say it to you if we were standing outside looking up. The sun has quietly loaded two of its most dangerous kinds of storm. One has already fired, and the shot is on its way here, timed to land on a holiday weekend. The bigger one, the one we were warned about, is still aimed at us and has not fired yet. Everything else tonight, every piece of physics, every historical comparison, every forecast, hangs off that one sentence. There is also a second half to this weekend that almost no one is connecting to the first, and I want to plant it now so it is waiting for you when we get there. At the same time this cloud is scheduled to arrive, the eastern half of the United States is forecast to be buried under one of the most extreme heat events in its recorded history. The kind of heat that drives every air conditioner in the country to full blast at the same moment. A geomagnetic storm stresses the power grid in one way. A record heat wave stresses it in a completely different way. And for reasons that have nothing to do with each other, no shared cause, no cosmic conspiracy, just the blind indifference of timing. Both of those stresses are going to land on the same power grid on the same weekend. We will get there. For now, just file it away. The sky is not the only thing that is going to be leaning on the wires this 4th of July. Let me walk you through the week as it actually unfolded, because the timeline is the part that makes this feel less like a random event and more like watching a fuse burn. On June 25th, the region we now call 4478 came around the eastern edge of the Sun, the way all spots rotate into view, and it was flagged almost immediately by the forecasters who watch these things, and by us, because even then it carried the early warning signs of a delta structure. That was the day we told you to remember it. Over the next several days it did not fade, the way most flagged regions quietly do. It strengthened. It grew larger and more tangled day after day, its magnetic field knotting tighter, until by the end of the month it was not just a region to watch, it was the dominant feature on the entire face of our star. And then, on the night of June 30th, while everyone's attention was fixed on the giant, the smaller region beside it, 4479, did the thing we had been braced for the big one to do. It snapped. In the span of about 16 minutes, its tangled field found a way to reconnect, and the reconnection released a burst of energy that our satellites registered as an X-class flare, the top of the scale. If you had been watching the right instruments in those minutes, you would have seen the sun's X-ray output leap upward, and then, in the imagery, a bright bloom over the region, and then, minutes later, a ring beginning to expand outward around the black disk of the sun. You would have been watching, in real time, the moment a piece of the sun tore loose and began its journey toward the calendar page marked the 4th of July. None of us felt it. That is the strange thing about these events. 1 billion tons of the sun blew off into space aimed at our planet, and here on the ground, in the evening of June 30th, nothing seemed different. The sun set the way it always does. But 8 minutes after the flare, on the daylit side of the world, radios faded, and in the days since, a cloud has been closing the distance, invisible, silent, and utterly indifferent to the fact that it is scheduled to arrive on a holiday. That gap between how ordinary the sky looked and how much was actually happening above it is exactly the gap this channel exists to close, because the events that matter most up there are almost never the ones you can feel down here, until suddenly they are. So here is where we are going. In a moment I am going to show you exactly what makes these two regions different from the thousands of ordinary spots that drift across the sun without ever threatening anything. Because once you understand what a delta region actually is, you will never look at a quiet-seeming sun the same way again. Then I am going to walk you through the anatomy of the shot that has already been fired, the X-class flare and the cloud behind it, so you understand precisely what is coming and precisely how we know it is coming for us. After that, we follow the cloud across 93 million miles of space to the moment it arrives. And then, at the end, we come back to the big one, the quiet one, the gun that has not fired. Because the flare that already went off is not the reason forecasters flagged this region a week ago. They flagged the big one, and the big one is still there. Part 2. What a delta region really is. To understand why two forecasters on opposite sides of the world both circled this same sunspot a week ago, you have to understand what a sunspot actually is, because almost everything you have been told about them is either wrong or so simplified that it hides the danger. A sunspot is not a hole, it is not a cooler patch of empty surface. It is a place where the sun's magnetic field has punched up through the surface so violently that it chokes off the normal flow of heat rising from below. The magnetism is so concentrated there that it acts like a lid, holding back the churning hot gas that would otherwise boil up to the surface, and because that patch is starved of the heat flowing up from underneath, it cools by a couple thousand degrees relative to everything around it. Cooler means dimmer. Dimmer, against the blinding brilliance of the rest of the sun, looks black. That black is not darkness. It is a spot so magnetically strangled that it only glows like a welding torch instead of like the surface of a star, and against the star it looks like ink. So when you look at a sunspot, you're not looking at a cold place. You're looking at the visible footprint of a magnetic structure reaching up out of the sun, a structure with a shape, with poles, with tension in it. And that is the key word, tension. Because the sun does not spin like a solid ball. Its equator rotates faster than its poles, and the whole thing is a fluid, so its magnetic field gets dragged and stretched and wound around itself over weeks and months until the field lines are coiled tight beneath the surface. Sunspots are where those coiled, overwound bundles break through, and how tangled the bundle is when it breaks through tells you everything about how dangerous it is going to be. This is where scientists use a classification that sounds like alphabet soup, but is actually a simple ladder of danger, and I want you to understand it, because it is the same ladder that told us 4478 was something to fear. At the bottom of the ladder is a class called Alpha. An alpha region is the simplest possible spot, a single dominant magnetic polarity, one knot of field poking through, tidy and stable. It is the equivalent of a still pond. Above that is Beta, which is a pair, a spot with a clear north polarity and a clear south polarity sitting side by side like the two ends of an ordinary bar magnet laid on a table. Beta regions are common and mostly well behaved. The field has somewhere sensible to go, from the north end to the south end, the way a magnet wants. Then the ladder starts to climb into dangerous country. Above Beta is Gamma, and a Gamma region is one where those neat north and south areas have stopped being neat. The polarities are mixed up, intertwined, no longer cleanly separated into this side and that side. The field lines connecting them are no longer taking a smooth, relaxed path. They are being forced to cross and weave to get from one polarity to another, and every time a field line is forced to cross another one instead of lying flat, energy gets stored in that crossing, the way a knot stores the effort you put into pulling it tight. And then, at the top of the ladder, there is the delta. A delta is not just mixed up polarities sitting near each other. A delta is when opposite magnetic polarities, a strong north and a strong south, get crammed so close together that they share the same dark core, jammed inside a single continuous spot with only a razor-thin line between them. Imagine forcing the north end of one powerful magnet and the south end of another into the same tiny box and holding them there. Everything in them wants to snap into alignment, wants to reconnect, wants to release. The only thing stopping it is that the surrounding structure is holding it all in place for now. A delta region is that box. It is opposite forces crushed together and held under enormous strain, and the entire configuration is sitting there waiting for something to give. When something does give, when those crushed together opposite fields finally find a way to reconnect, they release their stored energy all at once, in minutes, in a burst that can equal billions of the largest hydrogen bombs humanity has ever built. That burst is a solar flare, and here is the fact that matters most. Delta regions, the top rung of that ladder, are responsible for essentially all of the largest flares the Sun ever produces. The monsters, the record breakers, the events with their own names in the history books, almost every one of them came from a delta. So when a forecaster sees a region cross over into delta classification, they are not noting a curiosity. They are watching a loaded structure walk onto the stage. Now hold both of our characters up against that ladder. Region 4479, the smaller one, the one that already fired, is a delta. Region 4478, the giant, the one we warned you about, is also a delta. Both of them at the same time sitting on the Earth-facing side of the Sun, each one carrying an official daily probability of firing an X-class flare of about 1 in 10. Let me sit on that number for a second, because 1 in 10 does not sound frightening until you frame it properly. It means that on any given day, either one of these regions has roughly a 10% chance of producing the single most powerful category of explosion the Sun makes. 2 regions, 10% each. Every single day they stay turned toward us. Those odds compound with every sunrise. This is the part that is genuinely unusual, and I do not want to oversell it, so let me be precise about what is and is not rare here. Sunspots are common. We are near the peak of the Sun's 11-year cycle of activity, a period we have been calling Solar Cycle 25 on this channel for months now, and during a cycle peak the Sun is freckled with spots. Delta regions are less common, but they are not once-in-a-lifetime events either. What is unusual, the thing the forecasters keep noting in their own technical discussions with careful measured language, is having 2 large delta regions on the disk at the same time, both facing Earth, both capable. It is the difference between a table with 1 loaded weapon on it and a table with 2. Neither one may go off, but you do not look at that table and feel relaxed. And there is an asymmetry between our 2 that makes it worse, rather than better, and it is the same asymmetry I planted at the end of the last part, because it is going to run all the way through this story. The bigger region is the quieter one. 4479, the smaller delta, has been the busy one, snapping off flares, throwing the cloud that is now on its way to us. 4478, the giant, has been comparatively still. It produced one significant flare that came up just short of the major category, a flare catalogued as a C9.1, and otherwise it has mostly just sat there and grown, developing small delta features around its edges, getting more complex, storing more strain. And I want you to feel why that is unsettling instead of reassuring, because your instinct might be to relax about the quiet one. Do not. A large delta region that has not released a major flare is not a region that is safe. It is a region that is still holding everything it has wound up. When a region flares, it sheds some of that stored magnetic strain. It relaxes a little, like a spring letting go of part of its tension. A big, complex, magnetically wound-up region that has stayed quiet has not relaxed anything. It is the fullest version of itself. All of that stored energy is still in there, still crammed together, still held under strain, still waiting. The small one that already fired has at least spent some of its charge. The big one is fully loaded. That is why, when I look at these two regions, the one that scares me is not the one that already went off. It is the one that has not. Let me put it in terms you can hold on to, because the physics can get slippery and I never want to leave you behind. Picture two springs on a workbench, both wound down tight and held by a latch. One of them, the smaller spring, has already slipped its latch once, snapped forward, thrown something across the room and settled back down, still partly wound. The other spring is bigger, wound tighter, and its latch has not slipped at all. It is just sitting there, straining against the catch, perfectly still. Which one are you nervous standing next to? It is not the one that already went off. It is the silent one, because silence, in a structure that full, is not calm. It is a held breath. We have watched this sun getting louder for months. Those of you who have been with the channel through the spring remember the video we did back in May about one of the most violent solar eruptions of the whole year, and the one after it about a record-breaking radio burst that our instruments had almost never registered before. This is not the sun suddenly waking up out of nowhere. This is the continuation of a long, slow crescendo, a cycle climbing toward its peak, the surface growing more and more crowded with these wound-up structures. What is different this week is not that the sun got loud. It is that it loaded two of the dangerous kind at once, and one of them has already fired. Let me say a little more about the moment of release itself, the snap, because it is the most important event in this entire story, and it happens in a way that is genuinely counterintuitive. When those crushed together opposite fields finally reconnect, they do not slowly leak their energy. They find a shortcut, a place where a field line pointing one way can suddenly link with a field line pointing the opposite way, and the instant that link forms, the whole tense structure reorganizes itself into a lower energy shape, dumping the difference in a fraction of a second. Physicists call this magnetic reconnection, and it is the same fundamental process that powers the flare, powers the cloud, and, when the cloud reaches Earth, cracks open our own magnetic shield. It is the master key to this entire video. One process, happening on the Sun, and then again at the Earth, releasing stored magnetic energy by letting opposite fields find each other. Everything tonight is a variation on that single idea. Now, why is the Sun so full of these wound-up regions right now, in the summer of 2026? Because of where we are in the Sun's rhythm. Our star runs on a cycle of roughly 11 years, swinging from a quiet minimum when the surface can go days with barely a spot, to a raucous maximum when it is freckled with them, and then back down again. We have been tracking the current cycle, the 25th since record-keeping began, on this channel all year, and it has been running hotter than the official forecast predicted, producing more spots and more flares than the experts expected when it began. Near a cycle maximum, the Sun's internal magnetic field is at its most tangled, its most wound up, and it throws off complex regions like these far more often than it does during the quiet years. So the fact that we are looking at two large delta regions at once is not random bad luck falling out of a clear sky. It is the kind of thing this phase of the cycle produces, the Sun at the loud part of its song. Let me also give you the specific fingerprints of our two regions, because forecasters describe them with a shorthand that actually contains real information once you can read it. Region 4, 478, the giant, is catalogued with a spot classification that marks it as one of the largest and most developed types, a sprawling group with a mature structure, and it contains on the order of 28 individual spots knotted together across that 1450 millionths expanse. Region 4479, the smaller one that fired, is a slightly less sprawling but still substantial group, around 26 spots, covering roughly 700 millionths. When forecasters assign each of them that 10% daily chance of an X-class flare, they are not guessing. They are comparing the size, the complexity, and the recent behavior of these regions against decades of records of how regions with these exact characteristics have behaved before. A 10% daily X-flare probability is a statement grounded in history. Regions that look like this one have, in the past, produced an X-class flare on about 1 in 10 of the days they looked this way. It is the Sun's rap sheet, applied to 2 specific suspects. So we know what these regions are now. We know why they are dangerous, why 2 at once is the part that makes the professionals careful with their words, and why the quiet giant is the one worth losing sleep over. What we have not done yet is look closely at the shot that has already been fired. Because when 4479 let go on the night of June 30th, it did not just produce a flash of light. It produced a sequence of events, each one racing toward Earth on a different timeline, some of them arriving in minutes, some of them still days away as I am speaking to you. And to understand what is coming for the 4th of July, you need to understand exactly what happened in those few minutes on the surface of the Sun, and exactly how we can be so sure that a piece of it is headed straight for us. Let us go to the moment it fired. Part 3. Anatomy of the shot. At 50 minutes past 8 on the evening of June 30th, Universal Time, Region 4479 let go. The X-ray output of the Sun, which our satellites watch every second of every day, spiked upward in a matter of minutes and topped out in the X category, the highest class we have. The specific measurement was an X1.1. And before we go anywhere else, I want to teach you how to read that number, because once you can read it, every solar flare headline you ever see again will actually mean something to you instead of just sounding scary. Solar flares are sorted into letter classes, and the letters are a ladder where each rung is 10 times more powerful than the one below it. The gentle ones are Class A and Class B, so weak they barely register against the background hum of the Sun. Above those is Class C, flares strong enough to notice but too weak to affect us much down here. Above C is Class M, medium flares, the kind that can cause brief radio problems near the poles and put forecasters on alert. And then, at the top, is Class X. Each step from A to B to C to M to X multiplies the energy by 10. So an X flare is not a little stronger than an M flare. It is 10 times stronger than the strongest M, and 100 times stronger than a C, and on up the chain. X is the top of the ladder, the category with no rung above it. When you hear that the Sun produced an X-class flare, you are hearing that it produced its most powerful kind of explosion. Now, within that top category there is still a range, and this is where I owe you the honest framing I promised at the start. The X scale keeps counting upward. An X1 is the floor of the top category. There have been X2 flares, X5 flares, X9 flares. The Sun has produced flares estimated far above X20 in the historical record. So an X1.1 is genuinely the top class, and it is genuinely modest within that class. It is the smallest kind of the biggest kind. I am telling you that plainly because I never want you walking away from this channel thinking I dressed something up. This flare, on its own, by its own size, was not a catastrophe. What makes it matter is not how big the flash was. It is what the flash sent our way, and what its existence tells us about the 2 loaded regions that produced it. So let us follow what that flare did, because it did not do one thing. It did several, and they left the Sun on different timelines, and understanding those timelines is the whole game. The first thing the flare did reached Earth almost immediately, because the flare is, at its core, a burst of light. Not visible light mostly, but light at the high-energy end of the spectrum, X-rays and extreme ultraviolet. And light of any kind crosses the distance from the Sun to the Earth in about 8 minutes. So roughly 8 minutes after that region snapped, the X-rays arrived, and they slammed into the upper layers of our atmosphere on the daylight side of the planet, the side facing the Sun at that moment. When a flood of X-rays hits the upper atmosphere, it energizes and ionizes the air up there, and that charged, disturbed layer stops behaving like the calm mirror that long-distance radio signals normally bounce off of. Instead, it starts absorbing them. The result is called a radio blackout, and this flare produced a strong one, rated R3 on the 5-step scale we use for radio effects, logged right at the time of the flare on June 30th. Now, an R3 radio blackout is not something you noticed while you were watching television. It does not touch your phone or your internet, which run on entirely different systems, but it is very real for a specific set of people. Pilots flying long routes over the poles and the oceans, far from any tower, rely on high-frequency radio that works precisely by bouncing signals off that upper atmospheric layer, and during a strong blackout those signals can fade or drop out entirely on the daylit side of the Earth. Mariners far out at sea rely on the same kind of radio. Certain navigation systems degrade. For a little while, over the sunlit half of the planet, a slice of the radio spectrum simply goes dim. That is the flare reaching out and touching us, and it happened within minutes, days ago, before most people had any idea anything had occurred on the sun at all. But the radio blackout is the appetizer. It comes, it fades, it passes. The main course left the sun more slowly, and it is still on its way as I speak to you. Because when a region as wound up as 4479 finally reconnects its crushed-together magnetic fields, the explosion does not only make light, it can also blow a piece of the sun clean off. It launches a coronal mass ejection, a colossal cloud of the sun's own outer atmosphere, plasma threaded through with magnetic field, weighing on the order of 1 billion tons, blasted outward into space at millions of miles per hour. That is the cloud. That is the thing that actually crosses the gulf between the sun and us, and does the real work of a geomagnetic storm. And this flare launched one. Here is how we know it is coming for us, and it is genuinely clever, so let me walk you through it rather than just asserting it. We watch the space around the sun with instruments called coronagraphs, which work by placing a small disk over the blinding face of the sun, an artificial eclipse, so we can see the faint material erupting off it. When a cloud erupts off the side of the sun, heading off into space away from our line of sight, we see it in those instruments as a one-sided fan, blooming out to the left or the right. But when a cloud is aimed either directly toward us or directly away from us, we do not see a one-sided fan. We see it expand as a complete ring, a halo, growing outward evenly all the way around that artificial eclipse disk. That is exactly what appeared in the imagery late on June 30th, a full halo. A complete ring swelling out around the sun. A halo tells you the cloud is coming toward you or going away from you, and to break that tie, you look at where on the sun it came from. If a halo cloud erupts from a region near the edge of the sun, the geometry gets ambiguous. But this one erupted from a region sitting near the centre of the disk, the part of the sun aimed most directly at Earth. A full halo from a source near disk centre is the signature every space weather forecaster reads the same way. It means the cloud is coming here. And there is one more piece of evidence that seals it. As the flare erupted, our instruments detected a specific kind of radio signal called a Type 2 sweep, a tone that slides down in frequency over time, and that sliding tone is the fingerprint of a shock wave racing outward ahead of the cloud, ploughing through the thin gas around the sun. From that signal we can clock the speed, and the speed came in at roughly 1,496 kilometers per second. That is nearly 1 million miles per hour. That is the shock wave out in front of the thing that is coming. We even saw the scar it left behind. In the moments after the eruption, instruments watching the sun in extreme ultraviolet light recorded what is called dimming, a region of the sun's atmosphere that suddenly went darker because the material that had been glowing there a moment before was no longer there. It had been lifted off and thrown into space. When you see that dimming right where the halo launched, you are looking at the empty crater in the sun's atmosphere, where 1 billion tons of it used to be before it was hurled toward the Earth. All of these signatures, the halo, the central source, the Type 2 shock at nearly 1 million miles an hour, the dimming, they all point the same direction. They point at us. And this is where it gets more tangled, because this cloud is not arriving alone. In the days around this eruption, the sun threw off more than one cloud. There was an earlier eruption from around June 27th, whose cloud may brush past Earth first. There was more activity late on June 30th, and then there is this one, the headliner, the cloud from the X1.1, with its arrival forecast for the 3rd to the 4th of July. When multiple clouds are launched in sequence like this, they can arrive stacked up against each other, one ploughing into the wake of the last, and that pile-up can make the eventual disturbance at Earth stronger and longer lasting than any single cloud would have been on its own. So the picture is not one clean shot arriving on one clean day. It is a series of disturbances rolling in across the holiday weekend, with the main event timed for the 4th. Now let me pull us back and ground this, because I have just spent several minutes describing billion-ton clouds moving at 1,000,000 miles an hour, and I do not want to leave you with the wrong impression. This cloud from this flare is not a Carrington-level catastrophe barreling toward the power grid. The flare that made it was an X1, the floor of the top class. The storm that forecasters expect when it arrives is real but moderate, and we're going to spend the next part of this video walking through exactly what that moderate storm does when it gets here, the good and the concerning both. I'm not going to stand here and tell you the lights are going out on the 4th of July, because the data does not say that, and this channel follows the data. But I want you to hold two things in your head at the same time, because both of them are true, and the tension between them is the entire reason we are here. The first is that the specific shot already fired is modest, and the storm it brings will most likely be a light show and a nuisance, not a disaster. The second is that this modest shot came from the smaller of two loaded delta regions, the same class of region that has produced every solar catastrophe in recorded history, and the bigger one has not fired yet. The event that has happened is small. The configuration that produced it is not. Before we chase the cloud, I want you to understand how we know all of this, because it matters that none of what I am telling you is a guess. We are watching the sun right now with a fleet of instruments, each one built to see a different piece of the event. A pair of satellites in orbit around the Earth carry X-ray sensors that stare at the sun continuously, and it is those sensors that measured the flare and stamped it as an X1.1 at 50 minutes past 8 on the evening of June 30th. A separate spacecraft positioned to watch the space around the sun carries the coronagraph that caught the halo blooming outward after the flare. Another observatory images the sun in extreme ultraviolet light many times a minute, and it is that instrument that caught the dimming, the empty crater left behind. We are not inferring this eruption from a shadow. We are watching it, from several angles at once, with machines designed for exactly this. And those machines let us separate two very different kinds of threat that a flare can produce, a distinction that matters enormously for how worried to be, and it is one most coverage skips right over. The cloud, the coronal mass ejection, is the slow, heavy part, days away, the thing that causes the geomagnetic storm and the aurora. But a flare can also fling out a burst of individual particles, protons, accelerated to a large fraction of the speed of light, and those can arrive within minutes to hours, far ahead of the cloud. A flood of those energetic protons is called a radiation storm, and it is a different animal entirely. It is the kind of thing that matters for astronauts, for the electronics on satellites, for aircraft crews on polar routes. So the forecasters watch the proton count as closely as they watch everything else. And here is the reassuring part of this week's data, the part that keeps the current event in the moderate column. So far, the flood of energetic protons simply has not materialized. The proton levels measured near Earth have stayed at background, ordinary, quiet, well below the threshold that would count as even a minor radiation storm. What has been elevated is a different, gentler population, the high-energy electrons in near-Earth space, which climb to a peak of around 5,687 particle flux units, a moderately high reading that satellite operators note because, over time, those electrons can work their way into spacecraft electronics and cause subtle problems. But the dangerous protons, the radiation storm kind, have not shown up. Not yet. And I say not yet deliberately, because the forecasters expect the odds of a proton event to rise over the coming days, for reasons we will get to as the two regions rotate into a better aim position. For now, though, the honest read is a strong flash, a real cloud, elevated electrons and no radiation storm. The picture is active but not extreme, so let us follow the cloud. Let us leave the surface of the sun, cross the 93 million miles of empty space between there and here, and arrive at the moment on the 4th of July weekend when it finally reaches the Earth. Because what happens when a cloud like this touches our planet is one of the strangest and most beautiful pieces of physics in all of nature, and it explains everything from why your compass twitches to why the sky might catch fire over New York City this weekend. Part 4. When the cloud hits. The cloud that left the Sun on the night of June 30th has a long way to travel, and the trip itself is worth understanding, because it is the reason we get any warning at all. Light crosses from the Sun to the Earth in about 8 minutes, which is why the radio blackout hit almost instantly. But a coronal mass ejection is not light. It is matter, actual physical material, 1 billion tons of the Sun's own atmosphere, and matter cannot move at the speed of light. It lumbers. Even at the better part of 1 million miles an hour, a cloud like this one takes somewhere between 2 and 4 days to cross the 93 million miles between the Sun and us. That gap between the flash we see instantly and the cloud that arrives days later is the single most important thing standing between us and being caught completely off guard. It is our warning window. It is the only reason a forecaster can issue a storm watch before anything has actually happened here. For this cloud, from this flare, the forecasters have drawn that arrival window across the 3rd and 4th of July. But arrival is only half the story, and here is where the physics turns genuinely strange and genuinely beautiful. Whether this cloud does almost nothing to us or lights up half the sky does not depend mainly on how fast it is going or how much it weighs. It depends on which way it is facing when it gets here. And I mean that almost literally, like the orientation of a key sliding into a lock. The Earth is wrapped in its own magnetic field, an invisible shield generated far down in our planet's molten core that stretches far out into space and deflects most of what the Sun throws at us. That shield is the reason we are alive, the reason our atmosphere has not been stripped away over billions of years the way Mars lost most of its own. When a solar cloud arrives, it slams into that shield, and most of the time the shield does its job and shrugs the cloud aside. But the cloud is not just a blob of gas. It carries its own magnetic field, wound through it from the moment it tore off the Sun. And if the cloud's magnetic field happens to be pointing in the opposite direction, to the Earth's shield where they meet, specifically, if the cloud's field points southward while ours points northward, then the two fields do something remarkable. They link up, they reconnect, the same fundamental process that powered the flare in the first place, and that linking cracks the shield open and lets the cloud's energy pour in along the Earth's own magnetic field lines. Forecasters have a name for that crucial southward-pointing component of the cloud's field. They call it BES, and when they say BES has gone strongly southward, they are telling you the lock has turned and energy is flooding in. When BES stays northward, the shield holds and even a fast, massive cloud can wash over us with barely a ripple. This is why forecasting the strength of a geomagnetic storm is so maddeningly hard. We can see the cloud coming for days. We can measure its speed and its size. But the one thing that decides everything, the orientation of its magnetic field, we often cannot measure reliably until the cloud is about an hour from Earth. When it finally passes a spacecraft we keep parked upstream between us and the Sun. An hour. After days of watching it approach, the decisive detail only reveals itself in the final hour. As I speak to you, the solar wind streaming past Earth already shows the signs of disturbance from earlier activity. The total magnetic field strength elevated to around 18 nanotesla, and the B's already dipping southward to around -10 at times, with the wind itself flowing at roughly 400 to 425 kilometers per second. The door is already rattling. The main cloud has not even arrived. So what happens when it does arrive, and the lock turns? What does the storm forecasters expect actually do? The strength of a geomagnetic storm is measured on a scale that runs from G1, minor, up to G5, extreme, and for this event, for this weekend, the forecasters have issued a watch for a G2, moderate storm, peaking around the 3rd of July. Underneath that G scale is a more precise index called KP, which runs from 0 to 9 and measures how disturbed the Earth's magnetic field actually is, and the forecast has KP climbing to around 5.5, into that moderate storm range. I want to be straight with you about what a G2 does, because it is a real storm with real effects, and it is also not the end of the world, and both of those need to be true at once for you to understand this honestly. A G2 storm can cause voltage irregularities in power grids, particularly in systems at high latitudes, the kind of fluctuations that utility operators watch for and correct, but that do not, at this level, knock the lights out. It can increase the drag on satellites in low orbit, because the storm heats and puffs up the upper atmosphere so that spacecraft skimming its top edge feel a little more friction and drift slightly from where they should be, which is a headache for the people who track and steer thousands of satellites, but not a danger to you on the ground. It can cause high-frequency radio to fade at higher latitudes. These are genuine effects. They are the reason the watch gets issued and the reason satellite operators and grid managers pay attention. And they are, at the G2 level, manageable. This is a storm that the systems we depend on are built to ride out. But a G2 also gives something, and this is the part I actually want you to remember, because it might be visible from your own backyard. It gives us the Aurora. When the cloud's energy pours in along the Earth's magnetic field lines, those lines funnel the charged particles down toward the poles, where they crash into the gas of our upper atmosphere. And when those particles hit oxygen and nitrogen atoms high above the ground, they knock those atoms into an excited state, and as the atoms settle back down, they release that energy as light. Green from oxygen at one altitude, red from oxygen higher up, blues and purples from nitrogen. It is the exact same physics as a neon sign, an atom energized and then glowing as it relaxes, except the sign is 100 miles tall and stretches across a continent. That is the Aurora. That is the Northern Lights. It is the visible, beautiful, harmless face of the same storm that makes grid operators nervous. And here is the local hook for this particular storm. The forecast for this weekend, if the cloud arrives with its field oriented the right way, puts the Aurora potentially far enough south to be seen from places that almost never see it. The official watch language name states as far south as New York, Wisconsin, and Washington. Think about that. The same cloud thrown off by the strongest kind of explosion the sun makes, the cloud we have been tracking across 93 million miles, could end its journey by painting colour across the night sky over New York on a clear, dark 4th of July weekend. I want to be careful here and not overpromise, because whether it actually reaches that far south depends on everything we just discussed: the orientation, the timing, the pile-up of clouds, the darkness of your sky, and the luck of your weather. It may not get that far, but it might, and if you are somewhere across the northern tier of the country this weekend, away from city lights, it is worth looking north after dark. You could be looking at the tail end of the very event we're describing, and if you do go looking, let me give you the practical version, because there is a right way to hunt for an aurora. Get yourself away from city lights, as far from the glow of street lamps and buildings as you can manage, because light pollution will wash out a faint aurora completely. Give your eyes a good 20 minutes to adjust to the dark and then look toward the northern horizon, not straight overhead, because at these lower latitudes the glow tends to sit low in the north. And here is the trick most people do not know. Hold up your phone and take a long exposure photo of the northern sky, because a camera sensor gathers far more light than your eye can, and it will often reveal a wash of colour that is genuinely there even when you cannot quite make it out yourself. Now, I have been giving you the most likely story, the moderate storm, the light show, the manageable nuisance. But there is a reason forecasters are watching this weekend with more attention than a routine G2 would normally warrant, and it takes us right back to our two loaded regions and the thread running under everything tonight. Because both of those delta regions are not sitting still on the sun. The sun rotates, carrying its spots across the face we can see over the course of about 2 weeks, and right now both 4478 and 4479 are being carried from the central part of the disk toward the western edge. And the western part of the sun's disk is not a neutral position. It is, in a specific sense, the most dangerous place a flaring region can be pointed, at least when it comes to a certain kind of hazard. The reason has to do with the shape of the space between us and the sun. The sun's magnetic field does not stretch out to us in straight lines. Because the sun is spinning, its field gets wound into a giant spiral out through the solar system, a shape named after the physicist who first described it, the Parker spiral. And the Earth sits connected to the sun not by a straight line but along one of those spiral arms, which traces back to a spot on the western side of the sun's disk. So a region on the western part of the sun is, magnetically speaking, better wired to the Earth than a region in the centre. When a flare erupts from that well-connected western region, the fast-moving particles it accelerates can be funneled along that spiral highway and reach Earth more efficiently. This is why forecasters note that the odds of a radiation storm, a flood of energetic protons rather than a slow cloud, are actually forecast to rise over the next couple of days, up to around 1 in 5 by the 3rd of July, even though nothing new has erupted yet. It is not because the regions are getting more active. It is because they are rotating into the position where whatever they do next is aimed more squarely at us. Sit with the shape of that for a second, because it is the quiet engine under this whole story. The shot that has already been fired, the cloud arriving on the 4th, is only moderate. But the two regions that produced it are, day by day, rotating into the exact position from which their next shot would be better aimed at Earth than the last one was. The setup is not winding down. It is, if anything, improving from the sun's point of view and getting worse from ours. Every day those regions stay active and turn a little further toward that western sweet spot. The alignment for a well-targeted strike gets a little better, and the bigger of the two, the giant we were warned about, still has not fired. That is the escalation window. That is why a moderate storm forecast comes wrapped in more caution than the number alone would suggest. The most likely outcome this weekend is a light show and some grid operators earning their paychecks. The reason to keep watching is everything sitting behind that most likely outcome. Let me tell you about the 1 hour of warning, because it is a small miracle of engineering, and it is the reason a forecaster can tell a grid operator to brace before anything hits. About 1 million miles upstream from Earth, in the direction of the Sun, there is a special point in space where the gravity of the Earth and the gravity of the Sun balance in just the right way that a spacecraft parked there stays put, riding along with us as we orbit. We keep watchers there, probes that sit directly in the path of the incoming solar wind and sample it a little before it reaches us. When a cloud sweeps past those probes, they measure the one thing we cannot know any other way: the orientation of its magnetic field, that all-important north or south direction, and they radio the reading home at the speed of light. The cloud still has that last 1 million miles to cross, which buys us somewhere between 15 minutes and an hour of genuine, actionable warning. It is not much, but it is the difference between a grid operator watching a number climb and a grid operator being caught completely blind. And for the systems that can act quickly, that final hour is precious. There is also a seasonal twist to all of this that cuts this time slightly in our favour, and I want to mention it because it is the kind of honest detail that separates real forecasting from fear. Geomagnetic storms tend to couple into the Earth's field most efficiently around the spring and autumn equinoxes, in March and September, when the geometry between the Earth's tilt and the Sun's magnetic field lines up most favourably. This is a real, measured effect. We are not near an equinox right now. We are a week and a half past the June solstice, close to the least favourable time of year for that particular coupling. That does not cancel the storm, and it does not mean the Aurora will not appear, but it is a small thumb on the scale toward the calmer end of the forecast. One more reason the professionals are calling this a moderate event rather than a severe one. When I tell you the most likely outcome is a G2 and a light show, this is part of why. And it is worth putting a G2 in its proper place on the ladder, so the number lands correctly. The scale runs 1 through 5. A G2 is the second rung. The storms we will talk about later in this video, the ones with names in the history books, were G4s and G5s, the top of the ladder, tens of times more disruptive. A G2 by itself, in July, near the solstice, from an X1.1 flare, is a storm the modern world rides out without most people ever knowing it happened. I keep returning to that because I never want the size of the physics, the billion tons and the million miles an hour, to trick you into hearing catastrophe where the data says nuisance. The physics is enormous. The impact this weekend most likely is not. But before we get to the giant, before we come back to the gun that has not fired, I have to make good on a promise from the very first part of this video. Because the sky is not the only thing bearing down on the power grid this weekend. While the cloud is closing the last of its 93 million miles, something is happening in the atmosphere of the eastern United States that is going to lean on the very same wires from a completely different direction, for completely unrelated reasons, at almost exactly the same time. And when you put the two of them together on the same holiday weekend, you get the kind of coincidence this channel was built to notice. Part 5. The Other Threat, Same Weekend. While that cloud is closing the last of its distance to Earth, aimed at the power grid from 93 million miles away, the grid is being squeezed from the other side, from right here in our own atmosphere, and almost nobody is putting the two threats in the same sentence. So let me put them there, because the timing is the point. The same weekend the sun's cloud arrives, the eastern half of the United States is forecast to be trapped under one of the most extreme heat events in its recorded history. And extreme heat, it turns out, is one of the hardest things you can do to an electrical grid. Here is what is happening in the atmosphere. A dome of high pressure, technically a ridge, is building over the central and eastern part of the country, and it is not an ordinary summer ridge. Its strength, measured by how high it pushes a certain pressure level in the atmosphere, is running near the top of what has ever been recorded for early July, the kind of pattern meteorologists describe as several standard deviations above normal, which is a statistician's way of saying this is not supposed to happen. A ridge like that acts like a lid on a pot. It sinks air, compresses it, heats it, and it parks over a region and refuses to move, so the heat just builds and builds day after day with no relief. The forecast offices are not using cautious language about this one. They are openly writing about the possibility of all-time record high temperatures, not daily records, not records for the date, all-time records, the hottest it has ever been at some of these locations since records began. Let me give you the numbers, because they are the kind that stop you. In New York City, Central Park is forecast to reach 102 degrees Fahrenheit on both Thursday and Friday, the 2nd and 3rd of July. Central Park has not touched 100 degrees since 2012, but the daytime number is not even the part that should frighten you the most. The part that should frighten you is the night. On Thursday night, the forecast low, the coolest it is expected to get in the darkest hours before dawn, is around 85 degrees. If that holds, it would be the warmest low temperature ever recorded in New York City. Not the warmest for the date, the warmest period in the entire history of the record. I want to slow down on that, because it is the detail that reveals how dangerous this specific heat event is, and it connects directly to why the grid is in trouble. A heat wave does not kill people mainly through the afternoon high. The human body can endure a brutal afternoon if it gets a chance to cool down and recover overnight. What kills is when the night never cools. When the temperature stays in the mid-80s at 3 in the morning, the body never gets its recovery window, the core temperature never resets, and for the elderly, the sick, the very young, and anyone without air conditioning, the heat simply accumulates in the body night after night until it becomes lethal. The National Weather Service says it plainly in its own discussions. Heat kills more people than any other weather hazard, more than hurricanes, more than tornadoes, more than floods. And a heat wave with record warm nights, stretching across a densely populated corridor from the Midwest to the East Coast, with heat index values forecast between 105 and 115 degrees, is that killer in its most dangerous form. And think about who is actually at risk when a heat wave like this one settles in, because it sharpens why the grid matters so much. The people most vulnerable to a record heat wave are the elderly, the very young, the sick, and anyone without reliable air conditioning, which in practice means the poor, the isolated, and those living alone in older buildings that trap the heat. For every one of those people, air conditioning is not a comfort. It is the single thing standing between them and a genuine medical emergency, and during an event with record warm nights, it needs to run continuously, without interruption, for days, which means that the one thing you absolutely cannot afford during a heat wave of this severity is for the power to go out. A blackout in comfortable weather is an inconvenience. A blackout during a record heat wave on a night that will not fall below the mid-80s in a city full of people whose survival depends on their air conditioners is one of the deadliest things that can happen in an American summer. It has killed hundreds of people in single events in the past. That is the stake that turns this from a weather story into a grid story, and it is why the convergence I keep pointing at matters even though both threats, on their own, are probably survivable. The grid does not just need to stay up this weekend. It needs to stay up for the specific people for whom losing it would be fatal, during the exact days it is most stressed from two directions at once. Now connect it to the wires. When the night does not cool, the air conditioning never shuts off. Normally, even in a heat wave, demand for electricity ebbs overnight as temperatures drop and machines get a rest. But in an event like this, with the overnight temperature stuck near record highs, every air conditioner across half the country runs at full output around the clock for days, with no overnight break. That is peak electrical demand sustained, not for an afternoon but continuously across the holiday weekend. And peak sustained demand is exactly the condition under which a grid is most stressed, most loaded, closest to its limits, with the least spare capacity in reserve. Grid operators across the affected region will be watching their margins tighten for days, exactly the way they do in every major heat wave, managing a system running hot and hard, and that precisely is the weekend the sun chose to send its cloud. I want to be careful and honest here, the way I have tried to be all night, because it would be easy to tip this into something it is not. These two threats are not connected. The heat wave did not cause the solar flare. The solar storm is not making the heat worse. There is no hidden mechanism linking the sun's eruption to the atmospheric ridge, no cosmic hand arranging them together. It is a coincidence of timing, pure and blind. But a coincidence of timing is exactly the thing worth naming, because the grid does not care why it is being stressed. The grid only feels the load, and this weekend it will feel two different kinds of load at once. From the atmosphere, it feels record demand as the entire region runs its air conditioning flat out through record warm nights. And from space, it feels the geomagnetically induced currents of a moderate solar storm, those extra unwanted currents that a geomagnetic storm pushes through long transmission lines, the same phenomenon that, in far stronger storms, has actually collapsed grids in the past. One stress from below, one from above, landing on the same infrastructure in the same window. Let me put the honest bounds on it. Most likely both are managed. A G2 storm's induced currents are modest, and grid operators are experienced at riding out heat-driven demand peaks, and the probable outcome is that the lights stay on, and the two stresses pass without the public ever noticing they overlapped. I am not forecasting a blackout. The data does not support that, and I will not dress it up for you. But the reason this belongs in tonight's story, the reason it's not just a weather aside, is the pattern itself. This is what this channel exists to see. Two completely separate forces, one born in the atmosphere of the Earth and one born in the atmosphere of the Sun, arriving at the same fragile piece of human infrastructure on the same holiday, each one leaning on the wires in its own way, neither one knowing the other is there. Let me widen the lens on the heat for a moment, because New York is not alone, and the scale of this thing is part of what makes it a grid story rather than a local one. Down in Washington and Baltimore, the forecast has temperatures near or above 100 degrees for several days running, close enough that both cities could tie their longest streaks of consecutive 100-degree days ever recorded, a record that stands at 4 days. Out on Long Island, a location that has reached 100 degrees only a handful of times in more than 60 years of records, is forecast to get there this week. High in the atmosphere, the temperature at the level meteorologists watch is running among the top 5 warmest values ever measured over parts of the Northeast for this time of year. This is not a hot spell over one city. It is a single enormous dome of heat sitting over a corridor that holds tens of millions of people and an enormous share of the country's electrical demand, all of it pulling on the grid at once, all weekend, through nights that will not cool. And around the edges of that dome, the atmosphere is doing something else worth a mention, because it shows how much energy is loaded into this pattern. Along the northern and western rim of the heat, where the hot dome bumps against cooler air, lines of severe thunderstorms have been firing, the kind that produce damaging winds and large hail, a pattern forecasters sometimes call a ring of fire, because the storms trace the edge of the heat ridge like flames around a coal. Those storms are their own hazard to the grid, because a single line of severe wind can knock down transmission lines and cut power to a region in an instant, in the middle of a heat wave, at the worst possible time for anyone depending on air conditioning to survive the night. So the atmospheric side of this weekend is not one threat, but a cluster of them, all born from the same overheated pattern, all leaning on the same wires. Now hold that against the solar side, and let me name the specific mechanism by which a solar storm actually reaches into a power grid, because it is the hinge that connects the sky to the ground. When a geomagnetic storm disturbs the Earth's magnetic field, that shifting field induces electrical currents in any long conductor lying across the ground, and the longest conductors we have built are high-voltage transmission lines, hundreds of miles of wire strung across the continent. The storm pushes a slow, steady, direct current into lines that were built to carry alternating current, and that unwanted current flows into the giant transformers at the hearts of our substations, where it can cause them to overheat and misbehave. In a moderate storm, this is a manageable nuisance that operators watch and correct. In a severe one, as we will see, it is how an entire grid can come down. This weekend, the grid gets a dose of that induced current from the sun, at the same time it is straining under record demand from the heat. 2 hands on the same rope, and it ties straight back to the thread we have been following since the first minute. We started with a warning about a sunspot, a single dark region we were told to watch a week before it did anything. We followed its neighbour's shot across the solar system to this weekend, and now we find that the same weekend the shot arrives, the ground beneath us is loading the grid from the other side. The infrastructure that runs your life this 4th of July is caught, briefly, between the sky and the sun. That is the convergence, and it is only the near-term version of a much larger question, because a moderate storm arriving during a heatwave is a stress the system can almost certainly absorb. The real question, the one we keep circling, is what happens if the shot is not moderate? What happens if one of these regions fires something that is not a G2, but a G5? To answer that, we have to look at the times it has already happened, because the sun has done this before, and the last time it did, it set the sky on fire. Part 6. What the worst case looks like. A few weeks ago on this channel, we did a full breakdown of the worst case solar storm, the grid, the satellites, the whole nightmare scenario laid out end to end. If you want the complete version, it is there for you. Tonight I am going to give you the short version, and I am giving it to you now in the middle of this story for one specific reason. Because the region sitting on the sun tonight, 4478 and 4479, are the same class of region that produced every one of the events I am about to describe. Not a similar class, this same class, delta regions. When you hear what deltas have done in the past, you're not hearing about some exotic different kind of sun. You're hearing about the worst days of the exact configuration that is pointed at us right now. Let me take you back to the 1st of September, 1859. A British astronomer named Richard Carrington was sketching sunspots as he did most mornings when he saw something no one had ever recorded before. 2 brilliant points of white light flaring up over a large, complex sunspot group. So bright he thought at first his equipment had failed. He had just become the first human being to witness a solar flare, and what followed over the next day and a half is the benchmark against which every solar storm since has been measured. The cloud from that eruption reached Earth in about 17 hours, far faster than usual, because an earlier eruption had cleared the path ahead of it, and when it hit, the planet lit up. Auroras were seen not near the poles, but over Cuba, over Hawaii, over Colombia, close to the equator, so bright that gold miners in the Rocky Mountains woke up and started making breakfast, thinking it was dawn. People read newspapers by the light of the sky at midnight, and then the one piece of technology that 1859 possessed which could feel a geomagnetic storm began to fail. The telegraph, the world's first electrical network, went haywire across 2 continents. Operators received shocks from their equipment, telegraph paper caught fire, and in the strangest detail of all, some operators discovered they could disconnect their batteries entirely and keep sending messages using nothing but the electrical current the storm itself was inducing in the wires. The Earth's own Aurora was powering the telegraph. That is the Carrington event, the strongest geomagnetic storm in recorded history, and it came from a large, complex sunspot region, a delta. Now jump forward to May of 1921 to a storm often called the New York Railroad Storm. By then the world had more wires, and the storm found them. Telegraph and railway signalling systems failed across the United States and Europe. A signal tower and a railroad control building in New York caught fire. The storm is frequently cited as a rough once-a-century benchmark, a reminder that the Carrington level is not a one-time freak, but something the sun is capable of producing again on a timescale that means we are statistically overdue. And then comes the one that stopped being a story about telegraphs and became a story about us, about the modern world, about the grid you are relying on right now to keep this video playing. March of 1989. A powerful geomagnetic storm struck, and its induced current surged into the high-voltage power grid of Quebec. In the span of about 90 seconds, the entire Hydro-Quebec grid collapsed. 6 million people lost power. It stayed out for about 9 hours in the cold of a Canadian March. That was not 1859. That was a modern electrical grid, built by modern engineers, taken down from the sky in a minute and a half. And the storm that did it, while severe, was not even a Carrington-level event. It was smaller than what the sun is fully capable of. It just happened to hit a vulnerable grid at the wrong angle. Closer to our own time, in late October and early November of 2003, came a series of eruptions now called the Halloween storms, which included flares at the very top of the scale, one of them estimated around X17, more than 15 times stronger than the X-1.1 that just fired at us this week. Those storms rerouted aircraft away from polar paths, caused satellite operators to lose track of their spacecraft, damaged instruments, and knocked out power to about 50,000 people in southern Sweden. And most recently, in May of 2024, a storm that forecasters named after a space weather scientist reached the top of the scale, a G5, the first in about 2 decades. Many of you watching probably saw it yourselves because it pushed the Aurora down into places that had not seen it in a generation, across much of the United States, into Mexico, into parts of Europe that rarely see it. It was beautiful, and it was mostly harmless to the public, but behind the beauty it quietly disrupted precision GPS systems that farmers were relying on during planting season, nudging automated tractors off their rows, a small preview of how a modern, satellite-dependent civilization feels a storm it used to be able to ignore. And here is the statistic that should give you pause, the one that turns this history from a museum tour into a live concern. When scientists estimate how often a Carrington-scale storm actually occurs, the numbers they come back with are not comforting. The best estimates put the odds of a truly extreme, Carrington-class storm hitting Earth somewhere in the range of a low but real percentage per decade, which means that over the span of a human lifetime, the chance is not small at all. We have simply been lucky. The Carrington cloud of 1859 hit a world of telegraph wires. The largest storm of the modern satellite age, a monster that erupted in the summer of 2012, was every bit a Carrington-class event, and it crossed Earth's orbit and missed us only because the Earth happened to be on the other side of the Sun at the time. We passed through the crosshairs of a civilization-scale storm barely a decade ago and never knew it, because of nothing but the timing of our orbit, and every year that passes we have more to lose. The world of 1859 had telegraph wires and little else that a geomagnetic storm could touch. Our world runs on electricity end-to-end, threaded with satellites we cannot see and depend on completely, navigated by GPS timing signals woven into everything from banking to farming to the phone in your pocket. The more electrified and connected we become, the larger the target we present to exactly the kind of storm these regions produce. We are, in a real sense, more vulnerable to a Carrington today than we were the last time one actually hit. That is the uncomfortable trend running underneath all of this history, and it is why the people who study it do not treat these old storms as quaint. So line them up. 1859, telegraphs on fire and Aurora at the equator. 1921, signal towers burning. 1989, a modern grid down in 90 seconds and 6 million in the dark. 2003, satellites lost and a European city blacked out. 2024, tractors wandering off their rows across a continent. Every one of those events traces back to the same kind of magnetically tangled, wound-up sunspot region that produces the biggest flares. The same kind that is sitting on the sun tonight, 2 of them, both facing us. Let me linger on the Quebec collapse for a moment, because understanding exactly how it failed tells you what is actually at stake in the worst case, and it is not what most people imagine. People hear grid collapse and picture wires melting or sparks flying. That is not what happens. What happens is quieter, and in a way, more dangerous. The induced current from the storm floods into the enormous transformers that step voltage up and down at the substations, and because that current flows in one steady direction into machines built for current that reverses many times a second, it pushes the transformer's magnetic core into a state engineers call saturation. A saturated transformer stops behaving properly. It draws power it should not, it heats up, it distorts the current flowing through it, and it can trip the protective systems that are supposed to guard the grid. In Quebec, a cascade of those failures rippled through the system in about 90 seconds, and the whole thing fell over. Not with a bang. With a series of protective relays doing exactly what they were told to do, as the machinery underneath them was pushed outside the rules it was designed for. And here is the part that should genuinely concern anyone who thinks about resilience. The largest of those high-voltage transformers are not spare parts you keep in a warehouse. They are custom-built, each one the size of a house, weighing hundreds of tons, often manufactured to order with lead times measured in months or even years, and there are not many factories in the world that make them. In a moderate storm, none of this matters, because the currents are small and the transformers ride through it. But in a severe Carrington-scale storm, the fear among the people who study this is not a 9-hour outage like Quebec. It is that a truly extreme storm could damage many of those irreplaceable transformers at once, across a whole continent, and that replacing them could take not hours but months. That is the worst case. That is why a few weeks ago we spent an entire video on it. And the reason I'm reminding you of it now, in the middle of a story about a merely moderate storm, is that the regions capable of producing the severe version are not hypothetical. 2 of them are on the Sun tonight, and here is the thread I need you to carry out of this part, because it is the whole reason I brought you through this history in the middle of the story rather than at the end. None of those catastrophic storms started out looking obviously different from what is on the Sun right now. They started as large, complex Delta-class regions, exactly like the 2 we are watching. What separated a Carrington from an ordinary week was not some special, rare kind of sunspot that we would recognize as unique. It was 3 things. It was how hard the region finally snapped, how big the flare and the cloud turned out to be. It was which way the region was pointed when it fired, whether the cloud came straight at us. And it was the orientation of that cloud's magnetic field when it arrived, whether the lock turned. That is it. Those 3 variables are the entire difference between a light show and a blackout, and every one of those 3 variables is still undecided for the giant region we were warned about. We do not yet know how hard 4478 will snap, or whether it will snap at all before it rotates away. We do know it is turning day by day toward the western part of the Sun where a shot would be better aimed at us, and we would not know the orientation of its cloud's magnetic field until the final hour before arrival, if it ever fires one. The storm that has already been sent is a moderate one, a G2, a light show. But the region that scares the forecasters is not the one that sent it. It is the big one, still standing there, still loaded, still pointed at us. So let us finally go back to it. Let us look directly at the gun that has not fired. Part 7. The gun that hasn't fired. We have spent this whole video circling one region while looking at another. Every time I have described the flare, the cloud, the storm racing toward the 4th of July, I've been describing the work of 4479, the smaller of the 2, the second string player, and every time I have promised you we would come back to the giant, to 4478, to the one we were actually warned about a week ago. So let us go there now, and let us look at it honestly, because it is the reason this story is more than just another solar storm update, and it is the reason the word terrifying belongs in the title rather than merely dramatic. Here is the situation as it stands tonight. 4478 is the largest sunspot region on the entire visible face of the Sun. It has grown, over the past week, from that smudge on the eastern edge into a magnetic complex covering roughly 1450 millionths of the solar hemisphere, a structure classified at the very top of the danger ladder, a full delta. It carries a daily probability of firing an X-class flare of around 10%. And with all of that stored, tangled, wound-up energy, with all of that capability, it has, so far, stayed quiet. It produced 1 flare that came up just short of the major category, and otherwise it has simply sat there and grown more complex. It has not let go. Your instinct, and it is a completely human instinct, is to find that reassuring. The big scary one has been quiet, so maybe it is a gentle giant. Maybe it will just drift across the Sun and off the far edge without ever doing anything. I understand that instinct, and I need you to resist it, because in the physics of these regions, that instinct is exactly backward. When a sunspot region flares, it releases some of the magnetic strain it has been storing. It reconnects some of those crushed-together field lines, sheds some energy, and relaxes a little, the way a spring that slips its catch springs forward and settles into a looser coil. A region that has been flaring repeatedly, like 4479, has been bleeding off its stored energy in installments. It has spent some of its charge, but a large, complex Delta-class region that has stayed quiet has done the opposite. It has kept everything. Every bit of strain it has wound up over the past week is still in there, still crammed together, still held under tension by a structure that has not yet given way. Quiet, in a region that size and that complexity, does not mean safe. It means loaded. It means full. It means a held breath that has not yet been let out. That is why, of the 2 guns on the table, the one that worries the people who watch the Sun for a living is not the one that already went off. It is the silent one, the one that already fired at least discharged part of what it was holding. The silent giant is still holding all of it. Now add the clock, because there is a clock, and it cuts both ways. The sun rotates, carrying its spots from the eastern edge, across the face pointed at us, and off the western edge, over the course of about 2 weeks. 4478 has already made much of that journey. Over roughly the next several days, it will continue rotating toward the western edge of the disk, and then, eventually around it, out of our direct line of sight. And here is the double-edged part. On one hand, once it rotates around that western edge, it can no longer fire a cloud straight at us, and the immediate threat from it fades. On the other hand, remember what we learned about the Parker spiral, about the western part of the sun being the best connected position, the sweet spot from which a flare's particles are funneled most efficiently along the magnetic highway to Earth. So in the days right before it rotates away, 4478 passes through the most dangerous longitude it will ever occupy, the position from which a major flare would be most cleanly aimed at us. The clock is running down on the threat. But the final days on the clock are the most dangerous ones, so the honest picture, the one I can actually defend with the data, is a probability, not a prophecy, and I want to hold both ends of it up for you. On one end, the most likely outcome is genuinely undramatic. Most large delta regions, even scary ones, rotate across the sun and off the western edge without ever producing a Carrington. The 10% daily X-flare odds mean that on any given day, 90% of the time, nothing major happens. 4478 will very probably do what most regions do, grumble and flicker and drift away, and in 2 weeks it will be a footnote. That is the boring, likely truth, and I would be doing you a disservice not to say it clearly. But probability is a strange thing to live inside, because the unlikely outcome is not impossible. It is just unlikely. And when the unlikely outcome is a well-aimed X-class flare from the largest region on the sun during the exact days it is passing through the best-connected longitude, the stakes on that small probability are enormous. 10% a day, compounding across several days, from a region rotating into the sweet spot, is not a number you shrug off. It is a number you watch. It is the difference between the moderate storm we know is coming this weekend and the kind of storm we spent the last part of this video walking through, the kind with its own name in the history books. The shot that has been fired is a G2, a light show. The shot that has not been fired, the one still loaded in the Giant, is the one nobody can rule out. And this is where the title of tonight's video finally lands, where the word terrifying earns its place, and it is not where you might expect. The terrifying thing is not that a solar flare happened. Flares happen constantly. The terrifying thing is not even the cloud arriving on the 4th of July, because that cloud, we now understand, brings a manageable storm. The genuinely unsettling thing is the structure of the whole situation. We watched this region rotate into view. We named it. We told you, and forecasters told the world, a week in advance that it was a delta region worth fearing. And then, having been warned, having seen it coming with more clarity than we almost ever get, we are left in exactly the position we started in. We can watch it. We can measure it. We can tell you its size and its class and its daily odds, and we can do absolutely nothing to change what it does next. The warning did not give us power over it. It only gave us the ability to stand and watch a loaded structure 93 million miles away and wait to see whether it fires. That is the real weight of this story. Not the flare that came, but the one that might. Not the storm we can see arriving, but the region we were warned about that is still sitting there, still turned toward us, still holding its breath, and still, as of this moment, entirely beyond our reach. Let me make the escalation scenario concrete, not to frighten you, but because vague dread is useless and specific understanding is not. Suppose 4478, in one of the next few days, while it sits in that well-connected western longitude, fires a major flare, an X-class event several times stronger than the one its neighbour already produced. What actually changes? First, a stronger flare means a stronger radio blackout, potentially the top of that scale, a wider and longer fade of high-frequency radio across the daylit half of the planet. Second, and more importantly, a strong flare from that well-connected position could finally produce the radiation storm that this week has so far spared us. A flood of energetic protons racing along the magnetic highway to Earth. That is the population of particles that matters for the astronauts aboard the space station, who in a strong enough event retreat to the most shielded part of their spacecraft and wait it out. It matters for airlines, who reroute flights away from the poles where the radiation reaches deepest into the atmosphere. It matters for the electronics aboard the thousands of satellites we now depend on for everything from navigation to weather to the very communications carrying this video to you, The forecasters have actually quantified a piece of this, and it is the detail I keep coming back to. They put the odds of a minor radiation storm rising to around 1 in 5 by the 3rd of July, not because anything new has erupted, but purely because the two delta regions are rotating into that better connected position. Read that carefully. The forecast risk is going up while the sun does nothing new, simply because of geometry, because of where these regions are drifting. And if a larger cloud were launched from that position and arrived stacked on top of the clouds already inbound, the moderate storm we expect this weekend could be revised into something stronger. None of that is a prediction. All of it is a live possibility sitting on the table, and its probability is quietly climbing rather than falling. I want to be as clear as I can about the honest shape of this, because it would be easy to slide from possibility into prophecy, and I refuse to do that. The overwhelmingly most likely thing is that none of the severe scenario happens. 4478 most probably grumbles, flickers and rotates off the western edge in a week without ever firing its big shot, and the escalation odds, real as they are, describe an outcome that probably does not arrive. But probably is not certainly, and a 10% daily chance from the largest region on the Sun, compounding across several days as it turns into the sharpest firing position it will ever occupy, is precisely the kind of low probability, high-stakes situation that the people who guard the grid and the satellites do not get to ignore, and neither, I think, should you. Before we close, though, I owe you two loose threads, because this act of a sun does not just produce two neat regions and one clean shot. It produces noise, a whole restless background of smaller eruptions and flickering effects that fill in the picture of just how agitated our star is right now. And it produces a question, one I know a lot of you are already typing into the comments, about whether all of this activity up in the sky has anything to do with what has been happening down here in the ground this same week. Let us take both of those on, honestly, before we land this thing. Part 8. The Restless Sun and the Question. Everyone asks. Let me fill in the background noise because it tells you how agitated our star actually is right now, underneath the two headline regions. In the hours after the big X-class flare, region 4479 did not go quiet. It kept firing. Through the early hours of July 1st, it snapped off a whole swarm of smaller flares, more than a dozen of them in a single day, ranging across the medium, or M, category, with the strongest reaching about an M2.6. None of those individually as a headline. An M flare is a step below the X category, 10 times weaker, the kind of event that causes brief, minor radio fades near the poles and little else. But a dozen of them in a day, one after another, is not the behaviour of a sun settling down. It is the sound of a region that is still tangled, still reconnecting, still working through its stored energy in rapid installments. And each one of those M flares carried its own small radio effect, a flicker of high-frequency fade on the daylit side of the planet, so that the past day has been a near-constant low drumbeat of minor radio disturbances, punctuated by that one strong blackout when the big one fired. That is the texture of the sun tonight. Not one dramatic event and then silence, but a restless, crackling surface, two loaded giants, and a scatter of smaller flares going off around them, the whole Earth-facing side of the star lit up with activity. It is the backdrop against which those two delta regions are sitting, and it is worth seeing clearly, because it is the opposite of a calm sun that produced one freak flare. This is a sun that is genuinely worked up near the peak of its cycle, and the two regions we have been discussing are the most dangerous features on an already agitated surface. And a restless sun like this one is felt every day by a whole community of people you never think about, even on a week when nothing catastrophic happens. Amateur radio operators, the ones who bounce signals around the world off that upper atmospheric layer, live and die by solar activity, and a week of constant M flares means a week of signals fading in and out at the worst moments. The systems that provide precise GPS timing, the kind that farmers steering automated equipment and surveyors and even some financial networks depend on, wobble slightly when the upper atmosphere is disturbed by this much activity. Airlines watch it, because the polar routes that save them hours of flight time become risky when radiation and radio conditions degrade. None of these are headlines. None of them will make the evening news, but they are the constant low-grade tax that an active sun levies on a technological civilization, and this week the sun has been collecting flare after flare after flare, a dozen in a single day. It is worth remembering that the two loaded regions are not sitting on a calm star. They are sitting on a star that is already leaning on us, gently, all the time. Now let me turn to the question I know many of you have been holding, because I have seen it in the comments every time the Sun and the Earth get restless in the same week, and this week they did. Because at the same time all of this was happening on the Sun, the ground was moving too. Within the same 24-hour window as that X-class flare, the Earth produced two significant earthquakes on opposite sides of the Pacific, a magnitude 6 in the Gulf of California off the coast of Mexico, and a magnitude 6 near the eastern coast of Japan. And every time the sky and the ground stir at once like that, the question comes, reasonably, honestly, is the Sun doing this? Are solar storms triggering earthquakes? I want to take that question seriously, because it deserves to be taken seriously rather than mocked, and because the honest answer is more interesting than a flat no. The idea has an intuitive pull. The Sun is unleashing enormous energy. The Earth trembles the same week. Our minds are pattern-finding machines, and two dramatic events close together in time feel like they must be connected. Scientists have actually looked into this. There is published research probing whether there is any statistical relationship between solar activity or geomagnetic storms and the timing of earthquakes, and it is a legitimate area of investigation. People have run the numbers, looked for correlations, tested whether the Earth's seismicity ticks up when the Sun is active. And here is where the science actually lands, which is the part this channel will always give you straight. There is no established mechanism by which a solar storm could trigger an earthquake, and there is no convincing, reproducible evidence that it does. The reason comes down to energy and scale. A geomagnetic storm induces gentle electrical currents in long conductors near the Earth's surface, in power lines and pipelines, and the crust itself. Those currents are real, and they matter for the power grid. But the amount of physical force they deliver to the rock far underground, where earthquakes actually originate miles below the surface, is vanishingly small, many orders of magnitude too weak to move a fault. An earthquake is the release of stress that has been building in the rock for years, decades, centuries, as tectonic plates grind against each other, and when a fault is ready to slip, it slips because of that accumulated tectonic stress, not because of a whisper of electrical current induced from space. The faults, in the Gulf of California and off Japan, are two of the most seismically active places on the planet. They produce earthquakes constantly, all year, in every kind of space weather. Two of them happening during an active week on the Sun is what statisticians call coincidence, the ordinary overlap of two independently busy systems. It is worth understanding why the idea is so stubborn, because the reason is not stupidity. It is a real and reasonable intuition applied one step too far. We know that some external forces genuinely do move the Earth. The gravity of the Moon and the Sun raises tides not just in the oceans, but, measurably, in the solid rock of the planet itself, flexing the crust by small amounts twice a day. So it is not crazy to wonder whether a force from space could nudge a fault. The trouble is one of scale. The gravitational tides that flex the Earth are enormous compared to anything a geomagnetic storm delivers, and even those powerful tidal forces have only the faintest, most debated statistical whisper of influence on earthquake timing, and only on faults already right at the edge of failure. The electrical currents a solar storm induces in the ground are a rounding error next to the tides, and the tides themselves barely register. So the honest scientific position is not that the idea is silly. It is that we have looked, we understand the forces involved, and the numbers simply do not leave room for the Sun to be shaking the ground. So the honest answer is this. It is a fair question, precisely because the sky and the ground both stirred in the same week, and your instinct to connect them is a human and reasonable one. But when we follow the data, the connection dissolves. The earthquakes are the Earth doing what the Earth always does, driven by forces inside our own planet. The Sun is doing what the Sun always does near the peak of its cycle. They are two separate stories that happen to share a calendar, and the responsible thing, the thing that keeps this channel worth your trust, is to say so plainly rather than to stitch them into a pattern that the physics does not support. Let me give you the context that actually settles the earthquake question, because it is a number, and the number does the arguing better than I can. In the past 7 days, the Earth produced not 2 but around 98 earthquakes of magnitude 4.5 or greater, all over the planet in the ordinary course of a normal week. That is what our world does. It is a restless, fractured planet with tectonic plates in constant motion, and somewhere on it, A fault is slipping every single day. The two magnitude 6 events that happened to fall in the same window as the solar flare were not a signal rising out of the quiet. They were two entries on a long ordinary list in two of the most seismically active regions on Earth, that our attention naturally seized on because the sun happened to be dramatic that same week. Strip away the coincidence of the flare and they are just Tuesday on planet Earth. That is the honest statistical picture, and it is why researchers who have looked for a solar trigger keep coming back without a mechanism and without convincing evidence. The Earth did not need the sun's help to shake this week. It never does. There is one more piece of the restless sun picture worth naming, and it loops back to something we touched on earlier. That elevated population of high-energy electrons in near-Earth space, the ones that climb to around 5,687 particle flux units, has its own quiet nickname among the people who operate satellites. They sometimes call them killer electrons, not because they harm people, but because over hours and days they can seep into the interior of a spacecraft and build up a charge that eventually discharges like a tiny lightning bolt inside the electronics, occasionally damaging a satellite from the inside out. It is a slow, subtle hazard, nothing like the drama of a flare, and it is part of the reason an active sun is a constant low-grade management problem for the modern world, even on a week when nothing catastrophic happens. Every satellite operator on Earth has quietly been managing this elevated charge for the past several days, watching their spacecraft a little more closely than usual, nudging systems into safer states, and waiting for the levels to settle back down, all of it invisible to the rest of us on the ground. The noise is never truly harmless. It is just usually survivable, which brings us all the way back to the one thing this week that genuinely is aimed at us, the one connection that is not coincidence, the one thread that has run under this entire video. Because the earthquakes are not coming for us in any coordinated way, and the M-flares are just noise, but the cloud from that X-class flare is, right now, actually crossing the space between the sun and the Earth, actually timed to arrive on the 4th of July, actually pointed here. And behind it, the giant region we were warned about a week ago is still sitting on the face of the sun, still turned toward us, still loaded. That is the real signal in all this noise. That is what we should be watching. So let us land this, and let us land it on the thing that actually matters. Part 9. The Warning Shot. Let me pull the whole thread tight, because we have travelled a long way from that smudge on the edge of the sun, and I want you to see the shape of the entire thing at once. A week ago, on June 25th, a dark region rotated onto the Earth-facing side of the sun, and it was flagged, by forecasters and by us on this channel, as an incoming delta, a region to watch. Over the following days it grew into the largest sunspot group on the face of the sun, and crossed into the most dangerous magnetic configuration our star produces. Then, on the night of June 30th, its smaller neighbour fired an X-class flare and hurled a billion-ton cloud of magnetized plasma directly at Earth, timed to arrive on the 4th of July. That cloud brings a moderate storm, a G2, most likely a light show that could push the Aurora as far south as New York. Riding in on the same weekend, a record heat wave is loading the power grid from the other side, and behind all of it, the giant we were actually warned about still sits there, still turned toward us, still holding its charge, rotating slowly toward the one position from which its next shot would be aimed most cleanly at us. That is the whole story, and now I want to tell you what I think it actually means, because the title of this video promised you something terrifying, and I have spent 2 hours making sure you understand that the flare itself was modest, and the incoming storm is manageable. So where is the terror? It is not in any single number. It is in the shape of the thing. We were warned. That is the part that should sit with you. This was not the sun ambushing us out of a clear blue sky. A week before anything happened, the threat was identified, named, and described. We had for once something close to advance notice, and having been warned, having watched the region rotate into view and grow and complexify and load itself day by day, we arrive at this moment able to do precisely nothing except keep watching. We cannot reach out and calm that region. We cannot drain its stored energy or turn it away from us or make it fire early and gently instead of late and hard. We can measure it to 4 decimal places and we are completely powerless over it. The warning brought us the ability to brace, to harden a grid, to reposition a satellite, to look up at the right time. It did not buy us any control at all. And there is something genuinely humbling, maybe even terrifying, in that specific combination, in knowing exactly what is loaded and exactly where it is pointed, and being able to do nothing but wait. Think of the sun as a clock we can only half read. We know its rhythm in the broad strokes. We know it runs through a cycle of roughly 11 years, from quiet to violent and back, and we know we are near the top of the current one, the cycle we have been tracking on this channel all year, still climbing, still throwing off more of these tangled, dangerous regions as it goes. We can read the hour hand. What we cannot read is the minute, the second, the exact moment any one of these regions decides to let go, and how hard. 4478 might rotate off the western edge in a week and dissolve into nothing, and this whole episode becomes a story about a weekend with pretty auroras and a heatwave and a near-miss nobody remembers by August. Or it might, in one of the next few days, while it sits in that well-connected western longitude, snap the way its class of region has snapped before, in 1859 and 1921 and 1989, and send something at us that is not a light show. We do not get to know which. We only get to watch the clock and wait for the hand we cannot see to move. Let me be fair to the warning though, because I do not want to leave you feeling that it is worthless, just because we cannot reach up and calm the sun. A warning we cannot act on the source of is not the same as a warning we cannot act on at all. This is the part that actually matters, the part that makes all those satellites and forecasters and probes parked upstream worth every dollar. When forecasters see a cloud coming and issue a watch days in advance, the systems that keep our world running can brace. Grid operators can reduce the load on their most vulnerable transformers, postpone maintenance that would leave part of the network exposed, and position crews to respond. Satellite operators can put their spacecraft into a protective safe mode, powering down the sensitive systems most likely to be damaged and riding out the storm in a hardened state. Airlines can reroute flights away from the poles before the radiation arrives rather than after. Astronauts can move to the shielded core of their station. None of that stops the storm. All of it softens the blow. The warning does not give us power over the sun. It gives us power over how ready we are when the sun does what it was always going to do. And that, it turns out, is most of what preparedness has ever been. That is the real answer to the question I planted at the very beginning of this video, the question of what a warning is even worth when the trigger is 93 million miles beyond our reach. It is worth exactly the difference between being ready and being caught. This week, the sun handed us that difference a week in advance, and the systems that could brace have had time to brace. If the giant fires, we will not be able to stop it, but we will not be surprised by it either, and in the strange calculus of living next to a star, not being surprised is a large fraction of the whole game. And step back for a moment and see the larger arc this fits into, because tonight is not the end of anything. We are still climbing toward the peak of this solar cycle, or riding along its top, and the sun has been running louder than the forecast predicted from the start. The months ahead are likely to bring more of these regions, more of these flares, more of these clouds, more nights when the Aurora creeps further south than it should, and more mornings when a grid operator somewhere earns their paycheck quietly. 4478 and 4479 are not a finale. They are a particularly loud verse in a song the sun is going to keep singing for a while yet. What makes this week worth stopping for is not that it is unique. It is that it is a uniquely clear example of the whole pattern, laid out where we can see it. A region flagged in advance, a shot fired, a bigger gun still loaded, and a planet full of people who can watch it all in exquisite detail and change none of it. And maybe that is the honest place to leave you, because it is the truth of our whole relationship with the star we orbit. For all our satellites and our forecasts and our early warning spacecraft parked upstream in the solar wind, we are still, in the end, standing on a small planet watching an enormous nuclear furnace 93 million miles away, waiting to see what it does, warned but unable to answer. This week, it gave us more notice than it usually does. It flagged the danger a week out, fired a warning shot with its smaller weapon, and left the bigger one loaded and pointed our way. What we do with that notice, whether we harden the systems we can harden and look up at the sky we cannot control, is the only part of this that has ever been in our hands. Let me tell you what I am actually going to be watching over the next several days so you can watch it with me, because this story does not resolve tonight. It resolves over the coming week, one solar rotation at a time. I am going to be watching that daily X-ray plot from the satellites, the one that stamped the first flare as an X1.1, to see whether 4478 finally lets go while it still faces us. I am going to be watching the position of both regions as they drift toward the western edge, counting down the days until they pass through that best connected longitude and then, mercifully around the edge and out of our line of fire. I am going to be watching the proton counts to see whether that radiation storm the forecasters put at 1 in 5 odds actually shows up. And on the 3rd and 4th of July, I am going to be watching the readings from the probes parked upstream, waiting to see which way the cloud's magnetic field is pointing in that final hour, because that single number decides whether the 4th of July brings a quiet night or a sky full of colour over places that never see it. And I would gently ask you to hold, this whole time, the two truths that this story demands you carry at once, because the temptation is always to collapse into one or the other, and both of those collapses are a kind of lie. The first truth is that this specific event is moderate. The flare was the floor of the top class, the storm is a G2. The most likely outcome of this weekend is a light show, and some tired grid operators and nothing you will remember by the end of the month. If you walk away from tonight convinced the sky is falling, you have heard me wrong and you have heard the data wrong. The second truth is that the configuration that produced this moderate event is the same configuration that has produced every solar catastrophe in recorded history, that the larger of the two regions is still loaded and still turned toward us, and that its odds of firing something serious are quietly rising rather than falling as it rotates. If you walk away convinced there is nothing here worth watching, you have also heard me wrong. The honest posture, the one this channel tries to model every single day, is to hold both of those at the same time without flinching toward either the panic or the shrug. It is moderate, and it is loaded, both, at once. That is a genuinely difficult way to look at the world, holding the calm and the concern in the same hand, refusing to resolve the tension prematurely just because tension is uncomfortable. But it is the only honest way to stand next to a star. The sun is not trying to hurt us, and it is not looking out for us. It is simply enormous and violent and utterly indifferent, running through its cycle on a timescale that dwarfs our little calendars and holidays, and every so often it throws off a piece of itself that happens to intersect the tiny blue world we are standing on. Our whole job, the entire project of space weather, is to watch closely enough that when it does, we are not caught flat. So here is where we leave it tonight. The cloud is coming and it arrives on the 4th. The storm it brings is moderate, and the aurora may be beautiful, and the grid will most likely hold even with the heat leaning on it from the other side. But the region we were warned about is still there, still silent, still full. And silence, in a structure that size and that dangerous, is not peace. It is a held breath. We're going to be watching that region every single day it stays in view, and the moment it does anything, you will hear it here first. Because the warning we were given a week ago was never really about the shot that came, it was about the one that still hasn't. Keep your eyes on the sky this weekend, and keep them on the sun.